Okay, can everybody hear me well? So welcome back to this Friday session. And as we said on Wednesday and also last week, we are going to use these sessions to solve exercises. But today I'm going to sneak in some information and also some 10-15 minutes of an example which we are going to look at in more detail next week. And just to bring things together, if you wish to start with the next homework, we can do that. For those of you online, Shu Yu is going to help you with the exercises. And then I'm just going to float around here. And again, you can stay as long as you want if you have time. Abby is coming at 4 o'clock. So there should be 2 of us then. So just feel free to hang around as much as you want. You're always welcome to do that. Now, I just wanted to give you some quick messages because I got some emails about people asking, where are the videos? So if you, of the lectures, so everything is being recorded and put online. So if you go to one place where you find them, is on the main page of the GitHub address. And you will also find them on D2L. So if you scroll down on the schedule here, so in the schedule, you will typically find the videos which are being posted after the lectures. And these videos have also subtitles. I don't make them public on YouTube. They are unlisted, so you actually need the link to access them. And that's because I make them unlisted because this has with your privacy. If you don't wish to be on the video, you don't want to be made public, because sometimes it happens that some of you may end up, your name may be on the registration on Zoom. So being unlisted means that it's only you who have access to the link. Is that okay? So I don't make them public. But you have access to them. And you also have access to them via D2L. So that you will also find the same videos, the link to them. If you go to the this Jupyter book, which in a way contains all the teaching material. If you go to this one, and you click on schedule, then you will find the same videos. So this is being updated, and you can see, like last week, we have the videos and the handwritten notes. So you can always look back at the material at your own pace and whenever it fits you. And also remember, use the Slack channel, send us questions in case you have questions. Never hesitate to do that. Questions are always welcome. So what I'm going to do now is just to sneak in 10-15 minutes of theory, which then we are going to look also at into more detail next week. Any questions so far about practicalities, something which is unclear? Okay, goody. So let me quickly remind you of what we did on Wednesday, and then we are going to add a little bit more stuff to that. So the and I'm going to switch to the whiteboard. So let me do that. So on Wednesday, what we did was, one thing was to elaborate on the type of forces which are at play. And then we looked at the typical 2 ways which we are going to solve the equations. So in our case, we were just looking at a falling object with no air resistance. So the thing I'm going to add now is actually a simple model for air resistance. And we are going to look at this in 1 dimension. Now, the reason why I bring this up is that in 1 dimension, you can solve this by paper and pencil. You can actually find the position and the velocities, given the acceleration. In 2 dimensions, you cannot do it anymore. And if you look into the one of the exercises for next week, there is actually an exercise where you are setting up a 2 or 3 dimensional vector, where you can plot position or the acceleration in 2 or 3 dimensions. So when we are going to solve a differential equations in 2 dimensions, it's just going to be an additional dimension to the 1-dimensional case. But this is going to be one of the first cases you encounter where we cannot solve things by paper and pencil. But it depends on the type of model which we make for air resistance. So remember from discussion on Wednesday, we typically split the forces into fundamental forces and model forces. Many of the long-range forces, like gravitational force, they are fundamental forces, and we can derive laws of nature based on that. And then we have many of the contact forces where we simply have to rely on models. And a typical contact force is friction, where we don't have a fundamental theory for which gives us an analytical, nice, closed formula for the force. And then we have to rely on experiment. You get experimental data, and nowadays people use even AI and machine learning to use experimental data and to make a model for, let's say, friction. So we are going to look at different strategies for solving these problems. And what we did on Wednesday, the first thing, if we can integrate, we would do that. So we split a second order differential equation into two first order equations. The velocity is known. We have an expression for the velocity. No, sorry, I'm just ranting here. So we have an expression for the acceleration, which means that we know the derivative of the velocity. And based on that one, if we can integrate, like we did for the simple model, we can then get a nice expression for the velocity at a given time. And then we would integrate again here in order to get position. And by this two integrations, what we would end up with would be the final expression for the position here. Now, the other way by which we can solve the same equation is by a numerical approach. And the numerical approach is us starting with the same equations, but then we typically make a Taylor expansion. And in the Taylor expansion, we can decide where we truncate. Sometimes you have an expression for the second derivative, but in many cases, like for the velocity, we have only an expression for the first derivative, which is the acceleration. And that's what we can plug in to the differential equations. And then this delta t, which you see here, becomes a parameter where we can actually tune it. So if you make delta t smaller and smaller, then you're getting closer and closer to the derivative expression for the velocity, for instance. And when we do this kind of discretization, what we did on Wednesday was simply to drop these terms. And we assumed that we could truncate at just the delta t level, get this expression. And we could rewrite everything in terms of this expression here, where the derivative of the position is the velocity. And then we had the similar one for the velocity, where this expression here is given by the acceleration. So the kind of discretized equation which we end up with is something like this. And this is something we would implement numerically. So let me go back to the slides, because in the slides, you find the slides as a Jupyter notebook, was a standard PDF or just an HTML file. So let's just look at the Jupyter notebook and how you can encode this type of expression, because this becomes also useful for the next homework when you're actually going to set up a grid of velocities and positions. So let me just quickly change a little bit. And I'm going to go to the Jupyter notebook now. And this should be, let me just see where I did put it. Not the Google Chrome. There we are. So if you go to the lecture slides for this week, you will find the lecture slides as a PDF file or a standard HTML or as a Jupyter notebook. And this is just a Jupyter notebook we are looking at. And if you look at this specific example which we had, in this lecture notes, if you think that your Python programming is a little bit rusty, feel free to use these programs. And you can start using them as a kind of, template, and then you can plug in things. So what you would find is I like normally to often plot and save my results to specific folders, and this is what I do here. So I like to save the figure files, and you can use this if you want or not. I normally print it out as a PNG file. And if you look at the first example, this is just a falling object. And what I've defined is a T-final. As we went through in the lectures, we could calculate the T-final. I define a delta T step 0.1. And now what I do is that I arrange my T from 0 to a T-final in these steps delta T. So delta T is 0.1. Okay, so what I'm doing now, I'm setting up an array with values of time. So this is my discretized time. Are you familiar with this NumPy vector arrangement form? Good. So if you've forgotten about it, you can just look into these examples. And this is useful for the second homework and for the third one. And in this specific case, what happens now is that since T is an array, Y becomes an array, Y0 is just the initial position. And then here I'm just plotting it, or just actually printing it out. And you can see now the ball is falling from 10 meters and then gradually falling down, down, down. And after some time, when I make a plot here, you see now this is a function of time, it reaches ground. And that would be at your final time. So this is just a simple plot of this falling object, which we discussed in the lectures. Okay, so this is a way to visualize it. Then, when we did this numerically, what we would, as we went through on Wednesday, we would rewrite this in terms of this Euler's method. So let me just scroll down a little bit. And when we do that, this is just an example of where we plug in. So let me just bring down the numerical setup, which we discussed. So what we have is a discretized position. This is the Taylor expansion, which we saw on the whiteboard. And this is a Taylor expansion for velocity. This first term here is just the velocity. And this term here is the acceleration. And then we skip the high order terms. And these are the equations which we would typically implement. And when we discretize it, if you look at this equation here, this is what we have here. So you can decide whether you have this, how you define this delta T. You can fix it yourself. Just say delta T is 0.1. That's fully possible. Or you can set delta T equal the final time minus initial time divided by the number of integration points you want to use. So there are different ways of doing this. And if you scroll down a little bit, what I'm doing here, I'm finding the number of integration points. So I invite you to take a small look at some of these Python technicalities with the ceiling function, the ceil, which actually rounds up a given number. And then you have, so if I have 21.15, it gives you the smallest integer, not less than the input. And like here, if you have 21.75, it gives you 22. And then you have floor, which gives you the smallest integer close to that number, which when you have 21.75, it gives you 21. So what I'm doing here is to define the number of integration points as the final time, since the initial time is 0, divided by this delta T, which I have chosen. Alternatively, you could simply define n and then define delta T from n and the final time. And what you will find here is now an array for the time. And then I print an array for the acceleration, which I put to 0 in the beginning. So a NumPy array with zeros, which you can see here. And here you will find an example of how we could implement Euler's method. Now, there's a reason for why I bring this up. I'm going to repeat this next week and the week thereafter. So homework number 3, we're actually going to look at this falling object in 2 dimensions. And then we're going to refine it in homework 4, because then we're going to look at the bouncing ball. So we're going to add additional forces from the ground. And so you will see the ball bouncing up and down till it comes to rest. And you're going to simulate that. But the code which you see here, this is the kind of code, one code to the rule of them all. And in your case now, what you have to find is the acceleration. So if you look at the Euler's method, the way it's implemented, you would start a loop after you have defined time, acceleration, velocity, and position. You put all these to 0. You define initial velocity and initial position. And then you can also calculate the analytic expression. We are coming back to these things next week. But you see now the way you perform the analysis is going to be the same again and again and again. The only thing we are going to change is actually the algorithm for solving the equations, because Euler's algorithm doesn't conserve energy. And that's bad when you look at gravitational forces. But we can change it slightly with something which is called Euler-Kromer's method. But what you see here, if you look at the line which says expression for acceleration, throughout this course, when we are looking at different problems, the only thing you need to change is the force and then the acceleration. The rest doesn't care about what you plug in, as long as you have an expression for the acceleration. And you can do this in 1, 2, and 3 dimensions. So the update, instead of you integrating by paper and pencil, what you would do then is simply to update position and velocity by using one of these simple numerical schemes. So when I said in the beginning of the semester that you're going to have one code to rule all examples, this is the kind of movies I'm hooked on. Lord of the Rings, have you seen those movies? One ring to rule them all. So this is the kind of problem which you're going to see again and again. And in this case, we also have an analytical solution. And this is a kind of small exercise I'm going to give you over the weekend. You can look into the lecture notes. And I'm just going to stop pretty soon because I want to use the rest of the time on solving the exercises. But I wanted you to take a look at this specific problem. And the specific problem here is an object which now is falling in one dimension. We have minus g, which is the gravitational constant, the gravitational acceleration. But then we have made a model for the air resistance. So this will change depending on the velocity of the object which is falling. If the object falls fast, then experiment. So this equation you see now for the acceleration is an experimental quantity. So there is no fundamental law for it. So if the velocity is high, air resistance goes like velocity squared times a constant, which depends d, which will depend on temperature, air density, etc., etc. So these are just phenomenological forces, which are derived from experimental observations. If it's falling slowly, it will run like minus d or d times the velocity. In one dimension, we can integrate this. And this is actually where we're going to start on Monday. We will actually go through this example. So just take a look at it. But this is one of the cases where we can actually solve, again, a problem analytically. This is a standard textbook example. Have you seen this before in textbooks? Yes, I can see many people know it. So take a look at this over the weekend, because we will start here on Monday. And then we're going to look at how this problem transfers into 2 dimensions. And then you will quickly realize that in 2 dimensions, you cannot integrate analytically anymore. Does anyone see why this would happen in 2 dimensions? Anyone who can see that immediately? Let's take it as a small challenge. I can give you a hint here, because you would write the equations for the x component and the y component. Now, in this specific case, you're going to have a velocity which will depend on the x component and the y component. So when you integrate in the X direction, you depend also on the velocity in the Y direction. So you cannot decouple any longer the X and the Y degrees of freedom. So perhaps by some smart ways of integrating, you could find an analytical solution, but this is just an example of where you cannot find an analytical solution. And that's where the numerics will complement the paper and pencil work. So we're going to stress this throughout the semester, a little bit of this paper and pencil calculations and the numerical calculations. And hopefully that, again, gives you the tools to deepen your insights about physics. So this is where we will start on Monday. I'm going to stop here. We need the time to look at the exercise sets. And if you want to start with exercise set 2, feel free to do that, guys. And never hesitate to ask questions. That's why we are here. And Shu Yu is over there, as you can see. She will also peep into the people online. But we are just going to float around anyway. Okay, guys? I'm going to switch off the screen, if that's okay. And then we just work on the exercises. So for those of you online, I hope you still can hear me. So Shu Yu will keep an eye on you. I'm going to just take off the screen sharing, but we will have obviously the Zoom session open. And I hope you can use that. But then I'm going to stop the video as well here. And the recording will be posted online, as always.